this lecture first. Okay, guys. So what we have for you today is we are almost toward the end of the course. We have this lecture, and the next one will be our last. And the last topic that we are going to cover is within this handout over here. And this is a reason why I put week 10 and 11 in here, because I think that's the end of the road for us here. I cannot push toward the topics of magnetics. So that's always the case. Yeah. But as we spoke since the beginning of the course, that we going to go as fast as it needed to be. So we are not pushing anything at all. So you just learn as much as you can, given the time that we have. All right. So we just go as far as we go. Okay. So I hope that works. All right. So what we are going to learn today is we're going to extend the contents about the capacitance just a little bit more. So we're going to introduce to you some modification on top of the capacitors that we have already seen, and we knew how to calculate their capacitances. Okay, so that was good. But what we have for you more is something that is, I think, is more practical. So that means the real capacitors is going to do something like this, and that will be the first topic that we're going to cover. And once we have that, then we're going to eventually put that capacitor into something that you probably have learned back in the either middle school or high school physics or science, that you have a circuit. Okay, so you have electric circuit, and within that circuit you have current, electric current. So what we're going to sort of think of it like a review, we're going to go back and talk about electric current, and eventually, of course, it will lead you to Ohm's law. Okay, which I think you have heard a couple of times in the past. So we're going to review that a little bit and going to show you a simple electric circuit that use Ohm's law to calculate. Okay, but the main goal of mine is not Ohm's law applications anymore. I mean, well, it not like the scope of that is not only just the Ohm's law. What I really want for you to learn today is this, guys. Kirchhoff's rules. So this will extend the way that you can analyze a electric circuits. Okay, some of you might have done this already. For some of you haven't done this, this is going to be something new but easy to apply. That's kind of cool. Okay. So what you will learn here, once again, I will just have to use these tenses again, that even though you don't understand anything, you don't understand anything, but you will be given a recipe to follow. And if you follow the recipe correctly, you're going to get the answer. So that's how easy it is. And no more calculus here. So that's kind of nice. Okay. So that's what we are aiming for today. And once we learn that, then we're going to combine the electric circuits and having capacitors in it. And that will lead you to the last lecture on Saturday. We will be talking about the RC circuit. So that's what it's going to be our final topics that will be included in our exam. Sounds good? All right, guys. So let's get going here. So what else can we do with our capacitor that we learned last time? Okay, and what kind of extension that I need to show you here? So look at this one. So this is the simplest kind of capacitors, right? It's a parallel plate capacitor. And what you saw before, well, there's a space in between. It's just a blank space. And of course, you generate electric field, and electric field pointing starts from the positive charges and ends on the negative charges. And now you learn from Gauss's law, from everything, that you can execute those 3 steps process to calculate the capacitance of this capacitor. Cool? All right. Step number 1, you use Gauss's law to figure out the electric field. Once you get the electric field calculated, you use that one to calculate the potential difference across the plates. Once you have that, then you calculate the capacitance by taking the ratio between the charge over that potential difference, and you're done. Those are the 3 steps process, right? Now, the thing is this. What you saw was, if you would like to adjust the value of the C, just particularly for this parallel plates capacitor, if you remember, all right, we cannot flash back. Okay, I can write it down here. The C for this type of capacitor is epsilon naught, the size of the area of the plate, and the distance between the plates. Yeah. So, and we discussed last time that the only way that you can change the value of the C is just to change the physical appearance, the physical configuration of the capacitor. So, for example, you might want to enlarge your plate, or you might want to change the distance between the plates, on and on. So, what we got as a conclusion last time was the C, the capacitor, the capacitance depends on the physical shape of the capacitor, and hence the application on the touch screen with and without your fingers, you change the capacitance of that pixels, on and on, right? Now, what we have over here is this, but Ajahn, the space in between is really like a blank space, and there's nothing to support these whole two plates. I mean, of course, in reality, you can support it using something else. But in general, I mean, you don't like these two plates to touch, right? Because if these two touches, then of course, yeah, you're going to discharge everything, the charge will flow and neutralize everything, right? So in general, you want to keep the shape of your capacitor like this. Now you have a blank space in between. So you're wondering about, Ajahn, what if we want to like reinforce this kind of thing and keep this structure sort of like more rigid by squeezing in some material in between? Why not? That's cool. That's possible. But then what can be done even further is we can like use some sort of like a material that even help us to change something about the capacitance of the capacitor. So that means we just need to be a little bit clever picking the right kind of material that we want to put in between. Sounds like a good plan?
Okay.
Okay. And what kind of material that will help changing the value of the C or modify the value of the C? It turns out that material is named the dielectric material. Okay. What the dielectric means, it means like this, guys. So you guys remember water? Yeah, water. So it's a H2O. So you have H2O like this. Yeah, so I'm writing down like a chemical structure over here. And then, of course, water molecules is just neutral. That's no big deal. Well, that's fine. But in reality, when you look a little bit deeper, and if you still remember the terms electronegativity, I don't know if you're familiar with that. But anyway, the point is, it's in general, the oxygen has more electronegativity. And this is just another way of saying that electrons tend to spend more time around oxygen than hydrogen atoms. So what I'm saying over here is it means around the oxygen molecule is going to be a little bit more negative in comparison to the hydrogen side of the molecule. Okay, even though overall of the charges and everything add up to zero, but the distribution of the charge, negative one tends to go toward the oxygen side. So if I would like to represent this whole thing as just a simple, like using just a simple diagram, I can write it something like the negative part is on top and positive part in the bottom. Does that make sense? Or even better, I can even introduce some sort of like an arrow just pointing in the direction of, from negative to positive, just to give you the direction of the distribution of the charge in that molecule. Cool? Yeah, that's not bad. So in general, what you can name this kind of molecule, you might have heard of in terms of like a polar molecule. So there is a molecule that has some polarity in it. It's not like super neutral. It's not like zero charge everywhere. There will be some directional about the charge distribution built into that molecule. Okay. All right. So that's good. However, in just like a regular circumstances, those molecules, you can think of it water or whatever that has a polarity inside, they're just going to orient themselves randomly. So there's no control which direction of this distribution should this molecule be pointing to. So overall, it will go random. So you won't feel anything. That's fine. But then the interesting thing starts to build up if you place this type of material inside some external electric field. Here we go, guys. What do you think it will happen? What do you think? Whew. All right, don't have to think that much. Of course, we already learned that the positive charge try to move along the field, and the negative charge will try to move against the field, correct? So that means what you have happening here is the positive charge is trying to go to the right, and the negative charge is trying to go to the left. But because, of course, you cannot just separate the positive and negative part, I mean, the negative part of your molecule apart. That's impossible because I don't think that's strong enough. Well, of course, even though if you put in a very, very strong electric field, then you might be able to just like, dissociate them, but that's not the case here. So what you get over here is, of course, you're not going to sort of like break them into two parts or anything. So the best that it can do is just going to give you some rotation. Does that make sense? All right. So, I mean, it still keep the form of the molecule, but the only thing that happened is just like you turn the molecules because the positive one want to go in the same direction as the E. The negative portion of the molecule try to go against it, so you get a rotation. So those molecules will turn and try to align themselves with the external electric field. So you can think of the scenario is just like a compass within the magnetic field. Yeah, compass always point north, for example. So that was the compass that you place inside Earth magnetic field. Same thing over here. Now you have electric field. And then you have like an electric compass over here. It's trying to align with the electric fields. Cool. Okay. So with that, now what we can get out of this is here, guys. So let's imagine this. So let's consider like a cartoon version of this whole thing. When I say the cartoon, because in reality, you have like million of molecules, right? Don't forget we did like thermodynamics before. So the numbers of molecules in the material is going to be like gigantic. It's going to be like, 10 to the whatever Avogadro number or whatever. So this is a cartoon version. So what you have over here is once you apply external field, okay, so these molecules try to line up with the external field pointing from left to right as you are seeing over here. Now, what you can imagine is this. If you concentrate on the positive part of one molecule, it will stay next to the negative part of the neighboring molecules. Does that make sense? They are close. So that means these two are pretty much like in the same location, pretty much. So let me sort of like give you like an area over here. So, okay. And then if you look to the next one, well, Ajahn, from the look of it, the positive side of this one, it will stay very close to the negative side of the neighboring atoms, next one. So that means this positive and negative portion of the charge spend time at the same location around here. And then if you move on to the next, the same thing happens again. The positive side of this thing stay very close to the negative side of the neighboring atoms or molecules. So that means this area over here seems to be in the same location. And if you look at each location that I just highlighted, they are neutral because you have the same amount of positive charge and negative charge very close by. Okay, does that make sense? So with that, it means if you zoom out and you're trying to consider every place inside, so let me sort of like give you a boundary over here, inside the bulk of this material, the name is dielectric material, the bulk of the dielectric material, you can pretty much assume or overall and on average or in net or total or whatever you want to call it, the field in here is supposed to go to zero inside the dielectric material. Does that make sense? There will be only two places that you don't have any neighboring charges to cancel with. And those are, the one on the left ends of this and the right end of this material. So what I'm saying over here is just this, at the two boundaries of this dielectric material turns out to have no cancellation. So what it means at the end, all right, now I can erase all this crazy stuff here. Okay, so what you have over here is it's happening just like this in the bottom figure. So the leftover turns out to be just this, just on the surface of the dielectric material. If you're looking at the left surface, that would be just like a over negative. I mean, you have the surplus of negative charge on the left surface, and you have a leftover positive charge that you won't get any cancellation on the right surface. Does that make sense? You see the big picture now? However, when you have this, you have the negative layer of charge, you have the positive layer of charge side by side. they're definitely going to generate electric field as well. But if you notice, the direction of the field pointing from positive to negative, right, is now pointing in the opposite direction relative to the external field that is pointing from left to right. Isn't that cool?
Okay.
Right? You guys follow? So that means what I'm saying over here is once you squeeze the dielectric material in between, you have the induced field. Does that make sense? The electric field in green that got induced. Let me put E prime over here. Same thing as this one. Primed. So these are just the induced due to the original external field that you supply to the dielectric material. Okay. So what is going to be the net effect? The net effect that is going on is going to be, well done, I have only this much left over because the external field gets cancellation due to the induced electric field in green. Cool?
Okay.
All right. So that means when you look at the overall electric field in between two plates, now it's reduced. You only have this much left in between. So what's the point? Well done. So is it good or bad? It's good because of this. Remember, once the electric field is reduced, you guys know how to calculate the potential from the field, right? Because we already learned that the potential difference is just the negative integral E dot ds, right? We learned this one before. So that means when the E is reduced, the potential difference is going to be reduced as well because what? Of course, but then electric field is smaller. So the potential difference between two plates will get smaller as well.
Okay.
Cool? Not once we have that, Ajahn, okay, I got it. So that means the charge, if you don't changing any charge, all you did was just squeeze in the dielectric material. So that means the amount of charge on here stays the same. You're not changing any charge on there. So you can stay using the same Q divided by delta V. This is the definition of the capacitance. But now, because your delta V is reduced, you guys, what happened to the C? The C value will eventually increase, guys.
Okay.
Isn't that cool? So having the dielectric material squeezed in between, reduce the E, reducing the reduction of the E, reducing the delta V, the potential across. However, by having the smaller potential difference across, you increase the capacitance. And that's how it works. So that means without changing the physical parameters of the dielectric material, right? Because you're not extending the plate, you're not changing the distance between the plates. You just squeeze in the dielectric material, yeah, which is the film, and what you get is just bigger C.
Okay.
Cool. It's kind of convenient. All right. So what we have here is that is how you enhance or change your C by just put in the dielectric material in between. Now, the only question left is just how much bigger is that? How much do you get? So look at this one, okay? So the whole process now is no big deal, but then I just want to know how much bigger can you get? Now you're wondering, well, there's going to be some complications, I guess, but it's not. It turns out it's very simple.
Okay.
Look at this one. You guys still remember this expression over here. This is Gauss's law. Okay, the one on the left is just the amount of flux. You calculated flux by taking the dot product between the electric field and the area vectors. You integrate everywhere across your Gaussian surface. When you're done, you take this flux equal to the charge included inside divided by epsilon naught.
Okay.
Have you ever wondered why do you need this subscript here?
Wow.
Yeah, why do we need this subscript? Not all the time. Now here comes the answer, guys. So let's imagine this. So we have done the Coulomb's law since the beginning of this electric field topics and other stuff. If you have positive charge Q, and everyone knows it will generate electric field around. So just like, okay, pointing out, pointing out, pointing out, pointing out, pointing out. No problem. And if you are standing at a point, let me call it point P, and if the distance from the charge to point P is R, you say that electric field at that point is just 1 over 4 pi epsilon naught, that is just the K, times the charge generating the field divided by the distance square, right? No problem.
Okay.
This one is fine. Okay. Now here comes the question. What if I put this charge in the water? Oh, water is supposed to be blue. In water. Woo. So this charge is being placed in water. What do you think will happen? Woo. All right, there's a question coming. It doesn't matter how you put dielectric materials between two plates. It will always align with electric field. It doesn't matter how you put. It will align with them. Yes, I think so. Yeah, I think I understand your question correctly. So the molecule inside your dielectric material will try. I mean, I have to say try because we don't know the exact molecular structure of that dielectric material, but at least it will try to line up with the external electric field. Yes. But will it be a successful alignment? I don't know.
Okay.
Does that make sense? It's may I think I know they all try because it's just the effect from the electric field. The positive charge will try to follow the field, the negative charge will try to go against the field. So there will be some, some interaction going on. But maybe the structure of the dielectric material will just like, fix the location or fix the structure of the molecule. So it might not be able to align as it wants. So I don't know. My answer is maybe too broad. Just to take into account some possibility. That's what I'm saying. Okay, but yeah, they will try to align with the electric field. Yes. Okay. All right. So yeah, that's a good question actually. Yeah, they are trying. Yeah. Okay. All right. So come back to our question over here. What will happen if the charge Q is being placed in water? We haven't talked about that yet, right? And you haven't thought about that either, because what we calculated before was just like, okay, Ajahn, everything is like in a blank space. It's like a vacuum. There's nothing there. And here we go. This is the reveals of the whole thing. You just change that epsilon naught into, here we go. Oh, too much. Here. Turn it into epsilon of water. And you are done.
Okay.
It's too simple. So what I'm trying to say is the epsilon is trying to give you the constants that relate to the environment that the charge is in. The reason for having a naught as the subscript there is just saying that this charge is being placed in a vacuum. So if this charge is being placed in water, you just have to figure out what is the epsilon of the water, because that's why that's a name for it, right? It's a permittivity of something. And epsilon naught is the permittivity of free space. So if you have water, you have to figure out the epsilon, which is the permittivity of water. On and on and on. Okay? All right. So that's how easy it is. So Gauss's law will do the same thing. If you want to do the Gauss's law in water, sort of, you just change this into epsilon and you are good. That's it. But once again, Ajahn, so what are the value of epsilon? Actually, we can list like the value of the epsilon for each material. That's no big deal. But it turns out that's sort of like convention or whatever we already agreed. This is the way that we're going to do. We are going to introduce another constant for that material. We're going to call this the dielectric constant. Okay? And we can use kappa or we can use K, depends on the textbook. But the thing is, that dielectric constant is just the number that you will be able to use to multiply the original permittivity of free space, the epsilon naught, and will give you the epsilon of that material. Does that make sense?
Okay.
So this is good because it means that dielectric constant, it's like a relative parameter. It's sort of like it gives you the sense of how big is the epsilon in relationship with the original epsilon naught, the one in the vacuum. So let me show you the value of this one. On the next page, the table is listing the dielectric constants of some sort of like known, sort of like familiar materials. For example, actual air, of course, it's not perfectly one because you have some, gas molecules and other stuff there, but it's pretty close to one. So we can treat air as a vacuum. That's no big deal. Okay. Next one that is interesting is you look at the paper. Oh, paper is a little bit polar. So that means if you put paper in between your capacitor, you change something as well. And the dielectric constant is 3.5. Okay, what else that is interesting? You can look at this. Water. Woo, water, nice. It's huge. We know the water must be a big number because water is a very polar molecule, right? We already saw that one, the H2O thing. Yeah, it's highly polarized molecules, so it can change a lot under external electric field. And of course, you might have like a modern material, like some mixture of some, titanium ceramic or some weird exotic molecules or atoms. And as you can see, you can increase the K or the kappa, the dielectric constant, to like a huge, huge number here. Cool. All right. So what happened then? Now, once you already know what is the value of the dielectric constant, what's changed? Because the only thing that needs to be changed is just the epsilon. So whatever that you did before, we'll do the same. Here we go. Remember this one, guys? Last time we said the C capacitance of a parallel plates capacitor is simply epsilon naught A over D, right? Now you squeeze in some dielectric constant having the dielectric constant, sorry, my bad. Now you squeeze in some dielectric material with the dielectric constant kappa in there. All you need to change is this. It's a cap. Okay, let me write it like this. It's going to be, I don't know why I keep jumping here. Here, that's all you have to do. That's it, guys.
Okay.
Does that make sense? You just you just change your epsilon naught into the epsilon of that material. However, we just learned that you can figure out that epsilon by just taking the dielectric constant kappa multiplied by the epsilon naught. That's it. And you recognize that, okay, then this is your original C with the vacuum. So I can call this C to be C prime. That's a new one. And you can call that regular C, which is the air-filled capacitor. So what you get at the end is just the kappa times the original C. Does that make sense? So that's what you get out of this. Squeeze in the dielectric material. It will enhance or actually increase the capacitance of your capacitor by kappa times. And the kappa is just the dielectric constant of the material that you used in between your plates. And you are done.
Okay.
See, so I told you the conclusion is simple. All right, and this one is the one that I'm going to ask you in the final exams. Don't forget, check this out. All right, so I'm going to ask you to verify that the formula for the capacitance for a cylindrical capacitor, it looks like this. Okay, and now what you need to change here is if you squeeze in the dielectric material in between, you just fill up with some dielectric material. Yeah, let me put some green in there. And just like squeeze it in. So all you have to do is just taking that original expression and turn this into an epsilon of this material. But this epsilon of this one must be defined using some dielectric constants. So you just take the kappa epsilon naught and put it in the same expression there, and you are done.
Okay.
Wow.
Okay, so I hope you can find this to be simple enough, and the extension is just like no big deal at all. Sounds good? All right, so let's practice, like do a quick sort of like examples and see how it goes here. So you have a parallel plate air-filled capacitor has a capacitance of 50 picofarad. Yeah, pico is 10 to the negative 12. All right. Now, if each of its plates has an area given to be 0.25 square meter, what is the separation? Okay, part A is a straightforward plug and play question. We already knew that the capacitance of the parallel plate capacitor. So let me put like a C parallel here. This doesn't actually, you don't need that. Okay, let me put like a C over here. It's just epsilon naught A over D. Okay, so you want to figure out the D, the separation is going to be epsilon naught A over C. Epsilon naught is a constant. You can look it up. A is 0.25 square meter. And C, the capacitance is just 50 times 10 to the negative 12 farad. And that's it, guys. You are done. No big deal.
Okay.
Okay. Now, just to confirm, look at part B. If the region between the plates is now filled with material having the dielectric constant kappa of 5.6, what is the capacitance? So let me call this C prime. The new Y value is going to be kappa times C. And that's it. You're done.
Okay.
Is that too simple? All right. So the answer is it's going to be bigger 5.6 times relative to just having a parallel plate with an air field in between. Cool. See, I told you it's easy. All right. Next one, just double checking. Okay. Now you have an air-filled parallel plate capacitor has a capacitance given 1.3 picofarad. Now the separation of plates is doubled. The wax is now inserted between them. The capacitance turns out to be 2.6 picofarad. Find the dielectric constant of the wax. Cool? All right, so this one is like you have two scenario or two conditions, two situations, and you just want to compare them. The way that I usually like to approach is just list them out and compare. So let me call the first case to be air filled. Originally, let me call it the situation number one. So it's going to be C1 equal to epsilon naught, that's the air filled, times the A, you can call it A1 over D1. You can adjust everything. And then you do the same thing with the new scenario after insertion of the wax. So you're going to get the epsilon of the wax, mu A if you want, A2, and the mu separation D2 if you like. Okay, and what I can do is I can call this equation number one, this is equation number two. See, we're doing just like what we did back in the day of thermodynamic stuff. And what I'm doing is just taking the equation number two, dividing out the equation number one. So what you're getting is going to be C2 over C1 equal to, and now I'm just going to pair up the same type of parameter. So I'm going to get epsilon wax over epsilon naught, that's one pair. A2 over A1, that's the pair of the area of the plate. And then you're going to have D1 over D2, that is the pair of the separations between the plates. Cool? Because for this particular problems, you are not changing any value of the plate area. So those A2 and A1 just cancel. Okay, what else do you know? You said you double the plate separation. So that means the D2 must be twice the D1. So this is going to be twice the D1 because you double it. So that means this ratio over here will be 1/2. Okay, and what else? You already seen that the new value is 2.6 picofarads. Original is 0.3 picofarad. So on the left-hand side, the ratio is 2. Now the right-hand side, you can express your epsilon wax to be the kappa of the wax multiplied by the epsilon naught. That's what we agreed, right? How you write down the epsilon for any material. So that means epsilon naught cancel, you are left with just the kappa of the wax. Cool. And you have a factor 1/2 on the right side, and that's it. Your dielectric constant of the wax is 4, and you are done.
Okay.
No, not bad. So I hope introducing the dielectric material doesn't really give you any complexity whatsoever, right? And actually, it's a simple manipulation of the original capacitor to give you a bigger value very easily by picking the right type of material that you want to squeeze in. Okay, and you already increased the capacitance by kappa time. The kappa is dielectric constant. That's it.
Okay.
Wow.
Not bad. Okay, guys. So I have one more, which is about the coaxial cable. And because this one is in the configuration of the cylindrical capacitor, so I'm going to post this one as a DIY. All right. I'm going to have a question about the cylindrical shape capacitor in our final exam. And this one might be a follow-up question from that. So just a heads up here. Cool.
Okay.
Nice. Okay. So that's done for the business of capacitor, which is nice. All right. We're going to have a chance to bring this thing back and combine it into our circuits. And that will be the next stuff that we're going to do. So before the break, I would like to introduce or review for some of you that have already done this before about the electric current. Okay. So now we have done electrostatic before. So it means all the charges are stationary. But now we want them to move. They can travel because we have been talking about the conductor. We have talking about like, hey, if it's free to move, where it's going to move. But now what we want now is just we want some dynamics to be to happen. So we want them to move. So the way that you can express something that is moving, you talk about the current. And because this one is something, I mean, the thing that is traveling right now is the charge. So we are going to introduce electric current. Okay. And the concept is simple. It's flowing. It's flow. So you can make an analogy of the current flow to be exactly the same as the water flow. Okay. But instead of water, in water, you take the volume of water and you talk about the flow. You usually talk about how much water in volume that you will get per second. Does that make sense? Yeah. The flow rate of your water flow usually will be given in like cubic meter per second or something like that. So it must be the same thing here. But now we want the current flow. What is actually flowing? Yeah, charge. So the charge is flowing. And then when you want to take into account how many charges or how much charge are flowing, you usually have to think across some cross-sectional area or some surfaces. You can imagine this one very simply, or think of it like you have an open door and then you let the charge flow inside. Maybe you have like a room or something, and then you open up the door and then the charge is, flowing inside the room or something like that. And that cross section of that room, of that door will behave like a cross sectional area over here. And every time that there is one charge enter, then you count the amount of charge that going through that room, through that door. I'm confusing talking about this. Am I confusing you more or not? But anyway, the point is the cross sectional area of the door will be like an opening that allow you to count the amount of charge that is flowing through the door. Okay, so that's what it is. So what we want is we want to take into account the amount of charge that going through a cross-sectional area per unit time. So it's going to be charge per unit time. That's what we want. That is the definition of our current over here. So the current is just the total amount of charge per unit time, okay, that is crossing some cross-sectional area there. And look at the units, because the charge has a unit of Coulomb, time is in the unit of second, so current will have the units of Coulomb per second. But this one has an easy name that you can always refer to as ampere. So this is your familiar amp of any electrical devices that you usually mentioned. So that's it. It's a Coulomb per second that's give you the current flow. Okay. However, there's one quick note that I want to talk about. We already knew that most of the thing that is actually flowing is pretty much electrons, okay, negatively charged. But when we want to define the current flow, usually we define it along the positive things, right? Positive numbers, positive charge, all of the stuff. So the current direction, it's in the same direction as the movement of the positively charged particle. So if you want to talk about the negatively charged particle, such as electron here, it's going to move backward here. Okay, so it means if you have a negatively charged particle moved to your left, the current generated by that is going to your right. Okay. All right. But when you do circuit analysis, we don't really talk about electrons at this point, right? Just care about the currents. Okay. And usually we mention, talk about the current using I as the notation for the current flow. Cool. So far, so good. All right. So current is just a charge per unit time, right, through a cross-sectional area there. Now, what you have over here is to make currents flow. You already learned about this. The only way that it can flow, you need some potential difference. It's going to roll somewhere. Otherwise, it's going to stay exactly at the same spot, right? So that's why usually if you look at this one, you have a conductor. It could be like a wire. And if you would like to have a current flow like this, right? The current flow. And if you want to have it move from left to right, you're going to have to introduce the potential difference. Okay. And I don't know why, for some reason, I just want to note here again, when you talk about the circuits or some electric currents, they usually drop the delta. Okay. But you have to keep in mind all the time that every time you see V, most of the time it means delta V. It's always potential difference. Actually, it's 100%. It's 100 times. I mean, 100% of time that it's always potential difference. All right. So, but anyway, so we just had a special condition for the KQ over R where the zero potential is at infinity. So that's why, you know, okay. All right. Come back to this one. So whenever you see V, it's equivalent to the potential difference. And if you want the current to flow from left to right, you know that you want a high potential on the left and the low potential on the right. Cool. And another thing is, if you want a bigger flow, you want a bigger V. We know that. So imagine it's like V is just the height, right? That's the potential. Think of it like the height of this stuff. So if you want things to go sort of like fast or whatever, and you go to a higher place and then you jump down, something like that. So it seems like everyone agree that the bigger the V, the bigger the I. So that means you can draw a very quick relationship saying that the delta V, oops, what's going on here? The delta V is proportional to the I, or I is proportional to the delta V. And then you can turn this into an equation by introducing a constant, okay? I think I prefer I is proportional to V better. Okay, there you go. All right, something like that. And then I turn this into an equation, introducing a constant into it. Oh, that's my bad. Okay, there you go. There you go. All right. So what you have over here is you just write down the potential is linearly depends on the currents. Okay, and you introduce a constant to it. That constant R turns out, if you rearrange this one more time, R is the delta V over I, or you can write I as a delta V over R, up to you, right? There are only 3 elements in here. But the thing is, the R that you introduce here is inversely proportional to the I. So that means the bigger the R, the smaller your current is going to be. So that's why it seems like it's go opposite to the direction of, I mean, not opposite direction. It's going in the opposite sense to the amount of the current flow. That's why we name this R the resistance, because the bigger the resistance, the smaller the flow. Cool. All right. And the whole relationship about the potential difference, the current flow, and the resistance in any wire, we call this Ohm's law. I think you have heard of this one already. Okay, so you have Ohm's law in your hand talking about what is the relationship between these parameters: potential difference, current flow. The ratio give you the resistance. So that means the resistance over here is going to have a unit of volts. And amp that that I just introduced there. So the unit of the resistance is going to be volts per amp. And we have a special name for that. We call ohm. Okay, so that is the unit for our resistance there. And this is a figure showcase that this is a stuff that you probably have seen in, some circuit boards, or in, when you open up some electrical devices, you see like a bunch of this, I don't know, shape of what. Like, all right, but that's a yellowish, kind of like yellow brownish device in there. Those are resistors. Okay, so the resistors is the electrical device that contain the specific amounts of resistance on it. Okay, all right, so that's Ohm's law right there. And before the break, so I'm just going to show you a quick relation, sort of like consequence of knowing this Ohm's law is, hey, we already seen that there is a potential difference involved. And we already learned that every time you know the potential difference, you multiply by the charge, you get the energy. Simple, yeah? So that means, hey, every time that you have a resistor, oh, I'm sorry, let's talk about resistance, because it can be anything. So every time that you have a resistance, it's the part of the circuit that take away the energy in your system. I mean, out of your system. Okay, so that's why you're going to get some energy lost every time that you are going through some resistance. That's what happens. However, because we are looking at a charge that is flowing, it's already flowing. So we have a per unit time in our calculation. So instead of talking about just the energy, let's talk about the energy per unit time, per second. And that's why it leads you to power. Why not? Okay. So what you get over here is, let's talk about the power is the energy flow or energy transfer or energy movement. It's going to be the energy per unit time, but we already talked about that the energy can be calculated by taking the charge multiplied by potential difference. But then by definition, charge per unit time is just the current. So that means every time that you know the potential difference and you know the current that is flowing through that potential difference, the products between these two will give you directly the power that is dissipating through that portion of the circuit. Is that cool? Nice.
Okay.
So come back here. So now if you see, hey, Dan, I see the delta V here. I see there's a current flow here. So it means I can calculate the power that is going on within this part of the circuit, just taking I times V. Cool? All right. But the things has to happen if you have a resistor on, because you need Ohm's law there. All right, we're going to talk more about that later. But the thing is, it's a simple way of calculating how much energy is being lost at the location of the resistors, having a resistance R. And now you can manipulate this by using Ohm's law, P equal to IV, but I equal to V equal to IR. So you can turn this into I square R, or you can write I equal to V over R. You can turn this into V square over R if you like.
Okay.
Cool. All right. So this is easy one. And I think relate to something that you're familiar with is probably more like an adapter that you use in with your smartphones. You are rated by the wattage of your adapter, right? You might have like a fast charge. You have like a 20 watt adapter, 60 watt adapter. So if you look at the label on it, it will rate exactly how much current that is flowing. It could be like 1.2 amp, 2 amps or whatever. And then you have the voltage across. And if you take those two numbers and multiply, it will be very close to the spec of your adapter. It's IV right there. Okay. All right. So a quick example over here, and then we'll take a break. If you have a light bulb and it's marked on the box or the packaging, say that this light bulb is 2 watts and it's being operated at 1.5 volts. Now you are able to calculate the resistance of this bulb right away. So you say P equal to V squared over R. Just pick the one that you have information. Voltage is 1.5. Resistance is what you want. The power is 2 watts, and that's it. You can figure out the resistance of that light bulb easily now. Cool. All right, guys. So I think this is a good place to take a break.
Okay.
Yeah, sorry, it's a little bit over time. Guys, so okay, let's take 10. I'll see you. And then we're going to dive to the circuit analysis. Yeah, and then see how it goes. Okay, all right. See you in a bit. Okay, so what we have next is once we understand that, okay, when we have a resistor having a resistance on it, when we say resistors here, all right, you might be thinking about like an actual resistor that you found in like electrical circuits and everything, but in reality, no. Anything that takes away energy, because you guys know that everything that has resistance will take away some energy from the system or from the circuit. So that means the resistor here can mean anything. It can mean your smartphones, it can mean your refrigerator, your light bulb, and everything. So any devices that have resistor built in, it can be treated as a resistor. Does that make sense? Okay, so the key is resistance. Anything that has resistance in it, it can be modeled or it can be viewed as a resistor. Okay, so in conclusion, what we saw was like the electrical energy is transformed into thermal in resistor. So that means everything that has resistor, once you drive the current through, it will get hot. So this is the reason why when you use like, you know, your phone, playing games or whatever, things get hot when you drive a lot of current through, right? Because that's what it is. You're losing energy in form of thermal energy, okay? And because of that, if you would like to maintain the current, because you want the current to flow, and because once you get the current flow through some resistance, you lose that energy. So that means you must have some source of the energy that keeps supplying the energy to your system or to your circuits. Does that make sense? So that means you need a source of energy, okay? And that source of energy, we will call it its supply. Sometimes you call it electromotive force. But this one is like a historic name. It doesn't mean like we're not using it anymore, but we are still using it. But the way that you come up with the name, you have a force on it because back in the day, it's get the same feeling that you are supplying some force that pushing the charge and have it flow. Just like you have like a water flow, you need like a pump, right? You pump the water into a hose and then the hose can, you know, shoot the water up and all the stuff like that. So same thing over here. The source of energy will behave like a charge pump. It's pumping the charge and the charge allowed to move, okay? However, to think of it that way seems to me, it might be more natural to think of it like it's rolling or it's flowing. The reason I keep saying flowing many, many times because we learn about the potential, right? We know the potential difference. And we already knew that every time that you have like a mass, it's going to roll downhill all the time, right? The mass will go from high to low. So if you imagine this whole thing in terms of the electricity, so you have like a high potential here and you have a low potential down here. So the charge will try to follow that direction as well. It's going to go downhill. Same idea. So what I'm sort of like will give you an analogy is more like it. It's like when you go to a theme park or water park, you're playing a slider. So you slide downhill, right? At the starting point of the slider, you are starting at the high point and you let yourself ride down to the floor. That's low potential. And now if you want to play again, what do? You will have to walk up. But imagine that instead of walking up, you have an elevator that lifts you up here. And once you're there, now you're playing again. Okay, so this is acting as a source of energy. Does that make sense? Because that is the energy that allow you to lift yourself back up and then you start playing again. Same thing over here with the electricity. So if you have a potential difference, that's a delta V. So once you roll downhill, you come down here. You want to go back up, what do? You have to get some pump. You have to have a pump or you have something that lift that charge back up to a higher potential. So that's why you need a source. And that source will eventually drag this charge up to the top and you start rolling back downhill again. Cool? All right, so that's what the analogy that you can make with the mechanics that you had before. Because we have the same connections, it's a potential difference, or you can think of it like a potential energy, same thing. Okay, all right. So the way that you can provide this source, this is called EMF, and we have a symbol for it. We call it the E. So you might say that you supply the E to this to drag the charge upward and start rolling downhill again. Okay, so no doubt the E and the delta V seems to go hand in hand. It's the same thing. You introduce the EMF E is the same thing as, it's the same thing as you supply the potential difference equal to E across, something like that. All right, it will be better when you look at some examples. All right, but at least having this kind of analogy in your head might help. Okay, let's take a look what I'm saying over here. See, so we're going to look at a simple circuit here. Okay, so you have a circuit. When you have a circuit, means you have the whole complete picture of things that are going to travel in a loop like this. So you're starting from here, and you see a notation of this. This is your source. That's your pump right there. Okay, and sometimes you represent this in this symbol instead. That depends on the textbook. Okay, you can have this as a positive and negative one. The longer line that's represent a positive side of your source, and the shorter one represent the negative side. So what I'm saying means this is high, this is low. Okay, all right. Now you attach your positive terminal into an electrical wire. So this is just a wire, straight wire. So when you draw something like this, it means that portion of your circuit doesn't have any resistance. So we assume that the blue part of this one is zero resistance. Down here, there's no resistance whatsoever. And whenever you have to deal with a resistance, you introduce a symbol that looks like a zigzag portion of this one. That is the part of your circuits that give you a resistance. Okay? Okay. And this one is the symbol for a resistor. And I already told you, it doesn't need to be a resistor in your electrical circuits. This one could be a light bulb. It could be your oven. It could be your TV, radio, doesn't matter. Anything that has a resistance built in can be represented as a resistor. Cool? All right. So what happened here, guys? So you put in a source. You introduce a potential difference. So that means what you have over here is this is high, this is low. So what happening to the charge? The charge will start to slide downhill. See, sliding down. But then eventually you're going to come down here to the floor, and the source will pick that charge and pump it back up and start the whole process one more time. And that's why you call this a circuit, because it come in a loop, like, circuits, car racing or whatever. This is a circuit. But the thing is, what you need over here is you need to understand that the energy that's supplied by the source is being dissipated through this resistance part of this circuit right here. So that's where the energy is being used or being lost or being dissipated at the location of the resistance over here, resistor over here. Okay, so just to have you see the whole picture a little bit better, move on to the next slide. Here we go. This is what happened. Imagine this. So you have a source right here. Okay, so on the left is positive, on the right is negative. So it's high on the left and it's low on the right. Now, when you start at the top. So it means you come with the full energy. Nice. All right. So you start rolling, nothing happened. Energy stays the same. Now you hit the first resistance over there. So this resistance over here will eventually take away some energy. Okay. So the energy will drop by a little bit. How much? It depends on the potential across that portion of your resistor. There you go. Let me call it the V1. So the energy that you come in full gets dissipated by V1. And if you keep going, okay, just walking, right, keep going. Now you hit another resistor having the resistance R2. You are now have to figure out what is the potential across that part, because that potential is going to be dissipated again. So you lose another energy V2 down here. Cool. But by conservation of energy, these two amounts of V1 and V2 must eventually add up to the same amount of the energy that you supply in the first place. Does that make sense? All right. So that means what you have over here is, if we speak in terms of potential, not potential energy, they means the same thing, because potential is just energy per unit charge. So you can talk about energy or you can talk about potential. That will be fine. So you can think of like what we are speaking right now is like we are tracking like the charge, a test charge or something. Yeah. So what you have over here is that potential difference V1 plus V2 must be exactly the same as the potential across your source. Or if you multiply through by the charge that is flowing, QE equal to QV1 plus QV2, it's just the conservation of energy. The initial energy must be the same as the energy that you used up along the way. Isn't that cool? All right. So that's how simple it is to imagine what is going on. But then the question is, well, Ajahn, how much is that? Well, how much is this V1? Now, Ohm's law is very useful. See, every time that we have a resistance with current flowing through, right now the current flow through is this I. So you can always calculate the V1. Let me put like a notation here. Just say, hey, across the R1, the V1 over here will be just simply I times R1, and you are done. Isn't that easy? All right, that's Ohm's law. It's just Ohm's law. That's how you use it. You just use Ohm's law right away. Same thing over here. Look at the R2, but Ajahn, at the location of R2, there is a current, but the current stays the same because it's a water flow. It's same as water flow. If you come in with like a 10 Coulomb per second, that 10 Coulomb cannot be disappear, or you cannot have extra charge along the way. 10 must be 10 per second all the time. So the current flow in this case stays the same. And the potential across this will be just simply I times R2. Done. Very nice. And that's it. The current will just keep flowing and complete the circuit. Right? Now hit the negative ends of the terminal, get lift up higher, roll downhill again. And the whole process keep running in circle like this. Cool? All right, then. So that's not bad. So this is like a simple analysis of what's going on using Ohm's law. It's just a relationship between V, the I, and the R. That's very easy to use. But what we can get out of this example is this. When you look at this one, and then you say, but Ajahn, what if I have more than 2 resistors in our circuits? The analysis stays the same. So what you're seeing over here about now, Ajahn, I know how to deal with this. There is a current through resistor R1. There is a current through resistor R2, the current through resistor R3. So we can calculate the potential across each one of them. So across this one, you call it the V1. Across this one, you can call it V2. Across this one, you can call it V3. And V1 is just IR1, V2 is IR2, V3 is just IR3. How simple that is. And the sum of these three must be exactly the same as the energy that's supplied by the source. So that's why you say E is just IR1, IR2, IR3. And N, you can pull the currents out. And what you have left is just the sum of the R. And you can call that summation equivalence resistance. What does it mean? It means I can wrap these 3 resistors and put them into just a single one. The whole circuit will behave just like the same original circuits. This is the way that you analyze the circuits using the equivalent resistance way of calculation. So if you have even more than this, you just extend this formula through a larger amount of resistor, okay? The way that you connect these resistance together, we call it, you are put them in series because you put them back to back. The current that is flowing through are exactly the same because you have a single line, you have a single wire. So whatever the amount of charge that flow in, it must be exactly as it comes out. It cannot disappear. It cannot be added in the meantime. Sounds good? All right. So now you understand how you can simplify a resistor in series down into just single resistors. having equivalent resistance on it. But then you still have selections or options here. What if, I don't want to connect them back to back. I want to connect them, we call it in parallel. What does it mean by in parallel? Look at this one. Now you have R1 and R2, but now you take the left terminal and combine them into a single spot, junction A. And now you look at the right side of this one, you combine them into a single spot, that is junction B. So if you connect it this way, you are connecting in parallel. Okay, now what happened to this? Well, John, it could be more complicated, but it's not too bad. Think about it. If you have an incoming of a current I, once you hit the junction A, it has to split. The current has to somehow split. All right, how much? We'll see. But at least they have to split. But whatever you're going to split, the current that flow through the upper wire and the lower wire, once you add them, it must be equal to the original. It's a conservation of charge. So think of it like water. You come in with water, you have two pipes that break out. The water in two pipes add up must be equal to the original water from the original pipe. Yeah, same thing. So over here, you can say I must be equal to I1 plus I2. The current flow in must be equal to the current total flowing out. You are done.
Okay.
All right, so that's the quick thing that you can notice from this kind of connections. No need to clap there, actually. But what we have here is, with that conditions, it's called, it's not called, it's, you have the total current flow is conserved. But then now you look at the relationship between them. By having this connected in parallel, what about the potential across now? If you want to calculate the potential across R1, what do? You take the current multiplied by the resistor, right? So the delta V across this one, here we go, delta V1. This one is simply I1 R1. No big deal. What about the potential across R2? Let me call it delta V2. Of course, again, it's going to be I2 R2. But now here's the thing. We already learned about the potential or potential energy. These potential difference are path independent.
Okay.
So that means it doesn't matter if you want to go along the upper path or you want to go along the lower path. They must sharing the same potential difference. And that's why the final conclusion that you get out of this is delta V1 and delta V2 must be the same, because you are comparing between 2 points, exact same points, A and B. Potential difference must be the same number. Cool? All right. So with that idea, you can put this into work by saying that your potential difference of R1 and R2 must be equal to what? Electromotive force right here. What else can it be? Because junction A and junction B also connected to the source. So that's why I can say that your current I1 must be E over R1. Current I2 must be E over R2. Does that make sense, guys? Let's just reverse the equation a little bit. So let me put E over here. There you go. There. All right. So that means I am able to calculate the current flow on each wire, the upper and lower. And once I put that into this equation over here, see, I get E over R1 as a current I1, E over R2 as a current I2. Now you have a common factor E, I can pull it out. So what you see in the bracket, you can treat this one as, once again, an equivalent resistance. But because this is a reciprocal, you just say, okay, 1 over R equivalent equal to 1 over R1 and 1 over R2. And if you do that, you can reduce your circuit into, once again, a simply single resistor with one source. And you are done. Equivalent. There you go.
Okay.
I hope this concluded 2 things that you did in high school or maybe middle school science on the stuff that, hey, every time you are dealing with resistor, you have 2 ways of connecting them, either in series or in parallel. And if you go in series, you can sort of combine them into a single resistor with the equivalent resistance of the sum of all those resistances. Okay. Or if you want to connect them in parallel, you say that you can combine them into a single resistor, having a resistance following the reciprocal sum expression over here. Nice. Okay. So with that revision over here, so what I have to show you here is just I'm going to show you only one example because this is not what I want you to do today.
Okay.
This is just like a review of what we did last time. I mean, not last time. I mean, you have already done before, something like that. If not, then this is going to be like a quick recap of what happens back in the day of equivalent resistance. So I'm going to show you with this example just once, and we're going to move on to the stuff that I really want to show you. Okay, here we go. So if you have this setup over here, and the question A asks you to find out the equivalence resistance between point A and point B. And the second one is if they connect this one through a source that's supplying 34 volts, what will be the current flow in this? That is the question. Okay. All right. So the way that we do this is by considering the R equivalent of the whole thing. So what you can see over here is now, hey, Adan, 7 ohms and 10 ohms are connected in parallel. Okay, see that? Okay, so that means just by analyzing this part alone, I can put them into a single resistance first. So what I'm going to do is going to look like this. You have 4 ohms here. I'm going to put them into a single R equivalent here. And then I have 9 ohm here on the back. You guys with me? And because this one, I mean, these two in the middle are connected in parallel, that R equivalent that I have there must be found from the reciprocal sum expression. So it's going to be 1 over 7 plus 1 over 10. And it's going to be 17 over 70. And that leads you to R equivalent of 70 over 17. Cool? Done.
Okay.
Now, move on. Well, then we have these 3 resistors left. They are all in series connection now. Can you see that, right? So that means I can do one more step, combine this into a final single one. Let me call this R equivalent prime, the next equivalent resistance over here. And for this one, what I can do is just simply the sum of them. So what I'm getting over here is going to look like R equivalent prime is going to be 4 plus 70.17 numbers look so bad, plus 9. Okay, that's it, guys. So what I'm saying here is you can turn this set of resistor connecting like this down into just this. R equivalent prime 34 volt. See? And it's done. It's done in a sense that now you are able to calculate the current flow simply by I equal to 34 over R equivalent. And you are good to go.
Okay.
Okay. And with that current calculated, you will be able to trace back and calculate what should be the current that is flowing to in each resistor. So the answer is simple for the 4 ohms. The current that is flowing through 4 ohms must be I. So that's no big deal. That's I flowing through. And also 9 ohms must be the same I here because, I mean, current stays conserved in our circuits. The only complication probably here, because now you have junction. I mark as a blue dot right there. So that means once the current hit this junction, it has to split. I can name the upper one I1, the current down here I2 if I want to. But then those 2 I's must be recombined at the right side and give you back the current I at the end. So that's no big deal. So how can we calculate I1 and I2? Well, Ajahn, use the same trick because we know the potential either calculated through the upper path or the lower path will share the same potential difference. The upper potential difference can be calculated by V equal to IR, right? I times R. So that means from the top, the upper wire, what you can get is the V delta V equal to I1 times 7. But this I1 times 7 must be the same thing as if you want to calculate the potential difference through the bottom wire. And that is going to be I2 times 10. Does that make sense?
Okay.
Okay, so now you get an equation that say I17 equal to I2 times 10. You can call this equation number 1. However, everything must add up to the original I. So the equation number 2 that you have is I1 plus I2 must be equal to the original I. That is your second equation. Solving these two equations, you
Okay.
know which is which. How much current is flowing through 7 ohms, how much current is flowing through 10 ohms, and you're done. See, not too bad, right? Okay, so the thing is this, I don't want to do this anymore, right? Even I am teaching about this one is like, okay, it's like, okay, then we have serial connection, we have parallel connections, but eventually do we need to do this? To me, it's like, okay, it's too much already, all right? In the sense that I'm not going to give you like a unicorn shaped resistance connections and then, you know, condense it down into a single R. No, I'm not going to ask you this. What I'm going to teach you is this, and I think is more interesting. Plus, it gives you further sort of like applications of Ohm's law. Here we go. This one, don't want to do it anymore. However, it doesn't mean that you shouldn't do it. So I will take this one as a DIY. So please check this one out and see if you can answer this kind of question. Okay. So it's just more complicated, but it's not that bad. You still be able to do it using the same trick that we did before. But what I want you to see is this, guys. Now, what we learned from this lecture here allow you to conclude two things. At any junction, the currents flowing in must be equal to currents flowing out. You have seen this and you agree with this due to the charge conservation, right? This, we're going to name it a junction rule. It's a rule. It has to be total current in must be equal to current out. Total. No problem.
Okay.
And another thing that you learned from today's lecture and in the past, if you talk about the potential and somehow you go around the world and come back to the original position, everyone now know that there will be zero potential change. There is no potential difference. It's the same spot. It's path independent. So you won't get any change at all. So it means you can go around any loop as long as that loop is closed. And along the way, you calculated your potential difference, whatever you have gone through, V equal to IR or whatever, the sum must be equal to 0, no doubt. You cannot avoid that because that is the property of potential energy and potential. So we have this as a loop rule. The sum of the potential difference across any closed loop must be 0. These two rules combined into Kirchhoff's rule, guys.
Okay.
And I'm going to use this to do an analysis on a more complicated circuits, how it's supposed to be done. Just like a spoiler alert, what do I want to do? I want to do this problem, guys. Look at this. With this kind of setup, forget about it. You cannot use equivalent resistance to solve this anymore because you see all the resistors on here is not either in parallel or series, nothing. I mean, you cannot do anything. You cannot simplify these circuits anymore. How can you figure out the currents flowing through each resistor? Okay, the way to do it is by Kirchhoff's rules. Right here, guys. Okay, it turns out no matter what you do, the junction rule is simple. Currents in equal to currents out. Done. The more complicated one is just the loop rule, but it's not that complicated because I can classify the scenario that you're going to have to face into only 4 types. Here, come along with me. All right, almost done. Almost done. Just bear with me a little bit, guys. Okay. Here, if you look at point A and point B, and the scenario is you have a resistor with the current flowing through. And if I'm asking you, well, hey guys, what is the potential difference? So it means what is the VB minus VA? What should be your answer, guys? Well done. The current is flowing from left to right. So it means it must be high on the left and it must be low on the right in terms of the potential. So you know in your head, your result must be negative. You guys with me? Because V at B is lower than V at A. You're going to get a negative numbers out of this. How much? What is the negative value? We have already seen it. Every time you have a resistor with a resistance R, having the current flow through, the potential across is simply I times R from Ohm's law. So that's it, guys. I just say negative IR. You are done.
Okay.
You have another scenario that might happen if the current is flowing backward. Oh, if it's flowing this way, so it means it's going to be high on the right and it's going to be low on the left. So the potential difference from A to B, going from A to B, is going to be VB minus VA. Now it's going to be positive because you're going against the current. So you are walking uphill. Make sense? B is higher than A. So you are walking uphill. So that means at the end, you are standing at a higher potential. How much? IR again. Why not?
Okay.
Easy. This is easy, right? Try again. The other set of scenarios that you're going to face is you have to consider what is going on across the source. And this one is simple because look at this. Well done. Point A is connected to a negative terminal of the source. Point B is connected to the positive terminal of the source. So if you want to figure out the potential difference, VB minus VA, what will happen here, guys? Well, then of course, this is going to be high. This is going to be low because the B is attached to the positive ends of the terminal of the battery. The low, the point A is connected to the negative ends of your source or your battery. I haven't talked about battery before, right? I'm just like, hey, I haven't heard of battery today. Okay, so a type of source that you're familiar with is battery. So that's why sometimes it just came out of my mouth and the battery. Okay, so over here you can say, well, done. All right, it's going to be positive E. If the source giving you the electromotive force of E, so the potential across is going to be positive because from A to B, you're going uphill. You're going to a higher potential. And the opposite scenario is if point A is connected to a positive terminal of the source. So this is going to be high potential. This is going to be low. So the potential difference from A to B is going to be lower, negative E. And that's it, guys. What else can it be? Yeah, you only have this. So I'm going to show you quickly how can I apply these 4 scenarios to the real situation on the right. This is a very simple circuit, all right? So it's not that complicated just yet. So what I'm going to show you is this, guys. Let's consider this loop. This loop is A, B, C, D, A. So that means I'm going to go around this loop in this clockwise direction. So I am walking loop A, B, C, D, A. Okay, you guys with me? All right, I'm going to show you how to do the loop rule right now. Walking with me. Start from A. Now I'm hitting a source, a battery, and I'm trying to go from the negative terminal to the positive terminal. So by going across this one, the potential difference is going to be positive 6 volt. You guys with me? Potential difference. Keep walking. Now, because you don't really know exactly which current flow is. However, you can assume that the current is right now flowing clockwise. Let's take it. Okay, keep going. Nothing. Now you hit a resistor with the resistance of 8 ohms. Now you're walking down in the same direction as the current flow. So right now you are walking downhill because you're going with the flow of the currents. So what you have over here is going to be negative I times 8. You guys with me? V equal to IR, I times 8. But then because you're going downhill, because you're going with the currents flow, keep going. Nothing. Point C, turn. Now you hit a source at the positive terminal of the source. You're going from positive to negative. You're going downhill because you're going to a negative side of this. So you're going to a lower potential of negative 12 volt. Keep going. Nothing, 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 nothing. Turn. Now you hit R2. But now at R2, you have a current is flowing in the same direction as your analysis right now. So what you have over here is you are going along with the flow. So you are going toward the lower potential. So over here is going to be negative I times 10. You keep walking. Now you are done. You complete the whole loop. The sum of the delta V that you collected along the way must sum up equal to 0. And from this equation, you can figure out I equal to what, and you're done.
Okay.
Okay? And the reason that I don't really care which direction the current is supposed to flow, you can assume that the current is flow clockwise or counterclockwise, doesn't matter, because if your solution from this equation give you positive number, it just means that you assumes direction of the current is already correct. However, if it's reversed in direction, you're going to get exact same number, except your current is just turned negative. That's all. Okay, so the sign at the end of the your calculation will determine the actual directions of the current flow automatically. So you can assume the current to flow in any direction initially. You don't have to worry about it. Okay, sounds good?
Okay.
Good or not, I don't know. Now, I'm going to show you how to solve this problems. Okay, I summarize into a text over here, but I don't think it's easy for you to just read and understand things. Seeing an example is the easiest way to learn. So there you go. All right, so what I'm going to show you, I'm going to show you this time once, and I will have this one stick in your head for a couple of days, and I'll see each other again on Saturday, and I'll show you more so you get used to this whole thing. All right, and I guarantee you there must be this kind of question in the final exam for sure. So you will see once I complete this problem, you will see that you should be able to do this one on your own as well. Not difficult at all. So guys, take a look at this. Now, this is more complicated, but if you analyze it carefully, it's not that bad. The reason I say it's not that bad because of this. I can break this circuit into 3 parts. The part on the left, the reason I say this part is a single part because it's the part that doesn't have any junction. It's just a single wire connected all those R's and sources together, but it's a single path. It doesn't have any breakouts or anything. So this is good. And I can highlight the second portion of this one. That's my second wire that has like a straight line. Okay. And I can take this to be my third portion of my circuits right there. So I can break this circuit into 3 parts. Each part is just a single straight line, doesn't have any junction or whatsoever. But all those 3 parts combined at junction A and junction B, no doubt, that is fine. But the reason that I break this into 3 parts, because when you don't have any junction, the current in each wire stays the same. So that means I can assign the current flow in the yellow wire to be I1 if I like. And once again, I can put any direction to it. So it doesn't matter. I can say, hey, I1 pointing in this direction. Good. I can do the same thing with the green wire. It's a single wire. So I assume that the current flow on this one is I2 in this direction. I can pick any direction I like. Same thing with the third wire, the blue one. I can assume that the current flow is on this one is I3, pointing down. Cool. So far so good here. All right, so once I have that, now I'm going to show you how to apply Kirchhoff's rule based on those 2 rules, junction rule and loop rule. Take a look at this. I will find out what is going on at junction A. So at A, do you see what I'm seeing over here? There is an I1 flowing in, I2 is flowing in, and I3 is flowing out. Total in must be equal to total out. Total I in must be equal to total I out. So that means what I'm getting over here is it is I1 plus I2 equal to I3. I call this equation number 1. I'm done. Cool?
Okay.
But now you are seeing that now you have 3 unknowns, I1, I2, and I3. Single equation won't cut it. You need 2 more, right? So how can we create 2 more equations that allow us to solve all these 3 currents? Pick a loop.
Okay.
Just pick a loop because we are going to utilize the loop rule. So what I'm going to do is let me sort of like put some name into it. Let me call this corner M, N, O, and P. So can you see loop here? Well, John, there's so many loop. Yeah, that's why we name this type of circuits as a multi-loop circuit. There's one loop here, there's one loop there, and even like an outer loop here. So there are 3 loops that you can identify. Okay, so which loop would you like to try? I think I'm going to try the left-hand loop over here. So I'm going to go M, A, B, P, back to M. So I'm going to try that. So loop M, A, B, P, M. Okay? And now what I'm getting is I'm going to try to use the loop rule. Guys, I'm going to walk just like what we did before. I'm going to start from the upper left corner. That's my starting point of my loop. Let's go, guys. Go ahead. Okay, here we go. I'm just walking. I hit I1 with the R1. Oh, I have an R1, right? A resistance R1 with the current I1 flowing, but I am analyzing in the same direction as my as the current flow. So I am going toward a lower potential because I'm going in the direction of the current flow. So it's going to be negative I1 R1. You guys with me? Cool. Keep going, walking. Now I'm at A. Turn. Now I'm hitting R2, having the I3 currents flowing in the same direction. So I'm going downhill. I'm going to a lower potential of I3 R2. Cool. Keep going. Now I hit the positive terminal of E2. So I'm going from positive terminal to negative terminal. So I'm going to a lower potential. So it's going to be minus E2 there. Keep going. Now I'm at B. Turn. Now I'm seeing R1 with the I1 flowing through in the same direction. So I'm going to what lower potential. So it's going to be negative I1 R1. Cool. Keep going. Now I'm at P. Nothing. Now I'm hitting the negative terminal of my source. I'm jumping from negative to a higher positive terminal. So I'm going in a positive potential change of E1. Keep going. Now I'm arrived at the initial point M, completing the loop. The sum must be 0 according to loop rules, or according to potential difference must be 0 in any closed loop. And you are done. This is my second equation. Cool?
Okay.
So you start seeing what next we can do. It's not done yet because you need the third equation. So just pick another loop, shall we? And just to showcase that this can be any loop, I'm going to show you, I'm going to pick the right side loop. And now I'm going to loop in the counterclockwise fashion. Why not? All right, let's give it a shot. So I'm going to pick loop. Let's start from the upper right corner, N. I'm going to go N, A, M, P, B, O, back to N. So I'm going the bigger loop and I'm going counterclockwise. So I'm going to go N, A, M, P, B, O, N. This is a bigger loop there. All right. And let's walk with me, guys. Walking. Now I'm hitting R1 with the I2 in the same direction. So I'm going downhill. I2, R1. Keep going. A, nothing happened. Keep walking. Hitting R1. But now I'm going against I1. So I'm going uphill. So it's going to be positive I1, R1. Cool. Keep going. M, turn. Now I'm hitting positive terminal of the source. I'm going from positive to negative. I'm going to a lower potential, negative E1. Keep going. Nothing. Point P, nothing happened. Turn. I'm hitting R1 with the I1 going against me. So I'm going uphill. I1, R1. Keep going. Nothing happens. Turns at O. Now I'm hitting R1. But now at R1, I have I2, right? Because I2 has to go up like this. So I'm going along the direction of the current. So I'm going downhill. I'm going to a lower potential. So it's going to be negative I2 R1. I'm just keep walking. Now I'm seeing negative side of the source. So it's going to go to a positive side, higher potential, positive E2. Now I'm walking back to point N. Complete the loop. The sum of this whole thing must be equal to 0. And that is equation number 3.
Okay.
What I have to say here. And that's it, guys. Solving these 3 equations, you get I1, I2, and I3 equal to the. And once again, your final answers, of course, if they are positive, it means your assumed direction for all currents are correct. If some of this pointing in the opposite direction, the numbers that you got from this equation will be just negative numbers. That's all. All right, guys. So I think I'm going to stop right here. If you're still confused a little bit, just sort of like go back and, review it one more time. But if you still got confused, we will do more next time just to make sure that you seal the deal here and that you know how to deal with this kind of multi-loop circuits. Cool? All right, guys. That is it for today. Thank you.